As frontier AI models deploy across the global internet, they are structurally primed to favor cyber attackers over defenders. This chart shows the projected offense-defense balance over the next decade, based on a comprehensive survey of AI and security experts. For the next 2 to 5 years, the industry expects a severe widening deficit, where AI accelerates offensive capabilities faster than defensive ones. The data maps a recovery beginning at year 5, trending upward toward structural parity by the 10-year mark. This temporary deficit stems from a structural misalignment between how large language models operate and the rigid precision required for network defense. In cybersecurity, the goals of red teams and blue teams dictate entirely different margins of error. An attacker operating a malicious agent only needs a single exploit to breach a system. They can run millions of generations. If the AI hallucinates, writes broken code, or fails 1,000 times, the attacker loses nothing but compute cycles. A defender requires absolute precision. A false negative means a critical breach goes unnoticed, while a false positive can block legitimate traffic and take production servers offline. Attackers also dictate the speed of engagement. They launch exploits at the speed of inference. Defenders remain bottlenecked by operational realities. Patching requires dependency resolution, staging environments, and manual human validation across legacy systems. Frontier AI is inherently probabilistic. Its capacity to generate vast, randomized variations aligns with an attacker's need for volume, while challenging a defender's requirement for absolute reliability. This advantage is compounded by a concept known in security research as an equivalence class. This diagram shows an AI agent trained for automated penetration testing. It ingests raw source code and maps network vulnerabilities. Because the underlying capability is neutral, the exact same model that outputs a defensive patch can be trivially redirected to generate a targeted exploitation sequence. Consider AI-driven reverse engineering. A model trained to reconstruct high-level code from stripped binaries helps defenders analyze malware, but it also allows minimally resourced threat actors to quickly discover zero-day vulnerabilities in proprietary software. Because these capabilities belong to the same equivalence class, releasing powerful defensive AI into the wild immediately democratizes advanced exploit discovery for attackers. There is a prevalent assumption that high performance on standard software engineering benchmarks makes coding agents ready to automatically secure and patch vulnerable networks. Recent empirical evaluations test state-of-the-art coding agents against complex, security-specific environments rather than general programming tasks. These agents easily solve basic web vulnerabilities and simple capture-the-flag exercises, but when deployed into dynamic, real-world repositories, their success rate collapses. The primary point of failure is root cause analysis. If a vulnerability triggers a standard STAP trace, the agent can fix it. If the error is logical and distributed across multiple files in a massive codebase, the agent loses context and fails. Effective defense requires a cognitive architecture focused on security engineering, which demands deeper analysis than standard software development. Current agents suffer from 2 specific architectural bottlenecks. The first is a severe lack of flexible workflow planning. When tasked with analyzing an active environment, agents frequently get trapped in execution loops. They misconfigure standard tools like Metasploit and fail to adapt to the network connections they actively construct. This visualization shows the second major flaw, a lack of domain-specific integration. Current coding agents use standard terminals and basic linters, but they are missing critical security modules like Z3 solvers, dynamic fuzzers, and abstract syntax tree analysis. Without these specialized tools, an agent cannot map the implicit constraints of a program or execute the rigorous static program graphs required to trace the complex vulnerability back to its origin. Until AI agents are built with native interfaces for specialized security tooling, they will remain limited to basic code generation, incapable of managing enterprise defense. Compounding this agent failure is a severe deficit in accurate cybersecurity benchmarking. Many standard evaluations inadvertently allow models to bypass the intended security task. Agents often complete a prompt by finding an unintended logical shortcut in the test environment, rather than executing rigorous vulnerability analysis. Accurately measuring defensive capability requires end-to-end dynamic environments that replicate full production systems, complete with built-in mathematical verification mechanisms to confirm a patch actually worked. Without these highly constrained, executable testing environments, the industry risks overestimating the actual defensive capabilities of frontier models. Despite the current deficit, the long-term trajectory toward the 10-year mark shifts back toward the defender. Large organizations command superior computing resources, proprietary enterprise data, and priority access to advanced safety models. Capitalizing on those resources requires a specific architectural shift. This flowchart demonstrates the transition from a single LLM to a multi-agent pipeline. An LLM generates logical rules, feeds them into a traditional static analysis engine, and routes the feedback loop into a specialized reasoning model. To train these specialized reasoning models for security tasks, researchers deploy targeted reinforcement learning. The model is tasked with generating secure code, which is then immediately tested by a dynamic fuzzer. The successful compilation of a verifiable, secure patch serves as the explicit reward signal, forcing the model to prioritize functional security. Reaching parity requires transitioning AI from a standalone oracle into a tightly integrated component of a traditional program analysis pipeline. As these pipelines scale, evaluating them requires abandoning simple capture-the-flag exercises. Security teams must adopt layered, structured containment perimeters, often referred to as blue team sandboxes. Within these perimeters, models are subjected to dynamic blue teaming. They are forced to operate under worst-case adversarial scenarios, defending against simultaneous attack vectors to expose their breaking points. This testing dictates the deployment of strict system-level guardrails. An AI agent's access to external tool execution must be physically and logically isolated from the core production infrastructure it intends to defend. A model's security posture must be aggressively proven in a hostile, monitored sandbox before it is granted any operational agency in the real world. The definitive mechanism for breaking the attacker's volume advantage is formal verification. This is the process of proving with absolute mathematical certainty that a program's code aligns perfectly with its intended security constraints. Historically, formal verification has been too labor-intensive to scale across modern systems. It requires meticulous mathematical proofs that are difficult to produce for millions of lines of code. As specialized AI models mature, they will be deployed specifically to solve this scaling problem. Advanced AI will automatically generate the complex mathematical proofs and code invariants required for full system verification. This transition creates secure-by-design architectures. By mathematically eliminating entire classes of vulnerabilities, like memory leaks or buffer overflows, the sheer volume of an attacker's generated exploits becomes irrelevant. Utilizing AI to achieve mathematically provable structural defense represents the final state of cybersecurity, nullifying the vulnerability cycles that defined the previous decade.